Hi, this is ninth week, especially part A. We learn about chapter 4. This is network layer, and the network layer is explained in this layer for data plane. Also in chapter 5, that is explaining about the network layer, and that is mainly for the control plane. And we learn about that data plane and the control plane. This network layer is layer 3. First layer is physical layer. Second layer is data link layer. Third one, among 5 layers, this one is the middle one. And fourth layer is, as we learned already, transport layer. And fifth layer is application layer. Okay, let's move to the next. This chapter is composed of 4 sub-chapters. First one is explaining about the overview of network layer. As I mentioned already, a data plane and control plane. And here we learn about the architecture of a router. That is what is inside the router. We learn about this. In sub-chapter especially, 4.3, we learn about Internet protocol. This one is the highlight in this layer. This one is about the Internet protocol, and this one is explaining about datagram format and the fragmentation, IP version 4 addressing, and the network address translation. The acronym is NAT, and next version of the IP is IP version 6. And the final subchapter is generalized port and software-defined network. We learn about this one. This one is a new topic, and newly introduced in this 7th edition, and also 8th edition. This one is explained. Match and action and open flow examples of match plus action. In action, we learn about this. Okay, network layer. This one is explain about this. This one is chapter goals. We'll understand principles behind the network layer services, focusing on data plane after learning this network layer chapter. And this one is explain about the network layer service models and the porting versus routing, the main difference between them, and how a router works, and the generalized porting scheme we learn, and some example instantiation and implementation in the internet. We learn about this. Okay, network layer is transporting segment from sending to receiving host. And on sending side, encapsulates segments into datagrams before sending. And on receiving side, after receiving, this one is delivering segments to transport layer. And these network layer protocols are existing in every host as well as in router. This is host, another host here. This server, even this server is another host. And even this router, intermediate routers, those are called another host. Usually that is not called node. That is called as a node instead of host. There's all of them. We can call them node, and these computers are usually called host. And intermediate node, that is called, this one is router, mainly to route our packet to the final destination. And this router examines header fields in all IP datagrams passing through it, deliver to the appropriate destination. Okay, here two key network layer functions we learn here. First one is network layer functions, and among them, this forwarding is the first one we should understand. We learned already in the previous chapters. This one is moving simply packets from router's input to appropriate router output. That functionality is called forwarding. Routing functionality is more complicated functionality than simple forwarding functionality. This one is determining route taken by packets from source to destination. Here these routing algorithms are being used for the appropriate routing. We can think this analogy. Think about a trip. When we are taking a trip, forwarding means that is analogous to the process of getting through single interchange. And we are driving our car. We are going through some single interchange to go to the proper expressway. And the routing here, routing means, and this one is analogous to this process of planning trip from source to destination. This functionality is a kind of overall functionality from the beginning to the end. In our case, from source to destination. This network layer is divided into two planes. One is data plane and another one is control plane. This one is new concept, introduced the first time in 7th edition. Traditional router and traditional network layer we learned as one single one, and we learn about this later to compare simply. Here, data plane, we'll focus on this first. This one is local and per router function. Here, think about this. Router, like single interchange, determines how datagram arriving one router input port is forwarding to router output port. This is router input port, and for the final destination, that may be go out to this link 1 or link 2, depending upon that final destination. This is called forwarding functionality, like our interchange in expressway. And here another one is control plane. Those are network functionalities, and let's focus on this control plane. This one is network-wide logic, and this one is determining how datagram is routed among routers along end-to-end path from source host to destination host. We can think two control plane approaches. Traditional one, that is using this traditional routing algorithm, and that algorithm is implemented in routers. But newly introduced concept, that is software-defined network, acronym is SDN. This one is implemented in remote servers, in the centralized server, like this. Okay, not that, later. Let's look at this one first. This one is centralized one, centralized control plane. And we learn this one after this. Let's look at this one. This one is traditional router and per router control plane. Each router has that functionality, routing algorithm and some local forwarding table and to get the proper route, the routing algorithms are using other information from other routers, and that is called the routing information protocol, and they are exchanging. Okay, let's read this one first. Individual routing algorithm here, components in each and every router interact in the control plane. This part is called control plane. And this one is traditional single router. And each router is interacting with the other router, and they are exchanging the routing information. But conceptually, we are dividing. That is control plane, and porting functionality, that is data plane. Above one, that is routing functionality. To introduce a new concept, SDN, we are dividing this one. Because even though this one is traditional architecture, we'll learn about new architecture related to this one. All of them, those are centralized in a remote server, as we learned in the previous slide. Let's focus on this one. Values in arriving packet header here, and that is the destination information, destination address. Depending upon that, 0111, and that route, that is called forwarding. That link will be selected, and that will be forwarded. That output link is number 2. That is stored in this local forwarding table. Then which one is updating that information? This routing algorithm is doing that based on that information exchanged with others. Okay, this one is logically centralized control plane. This one is control plane. A distinct, typically remote controller interacts with the local control agent. This one is interacting. That is different from the previous one. And that can be centralized. And that may be learning even in a single server, or in different servers that may be learning, but let's try to make it simplified. Let's assume this one is learning in the single server, in the centralized control plane here. This one is data plane. And in the same way, if that packet is arriving here, then depending upon that final destination, this one is each control agent. This one is control agent. Simply, this one is very simple node. This one is simply forwarding that packet to this link. And this remote controller will update that forwarding table. And they are centralized. That's the main difference between this one and previous one. And let's look at some architecture of a router. This subchapter is explaining about that. What is inside a router? If we are using this block diagram, functional block diagram, we can understand the architecture of a router. This one is very similar to the special purpose computer architecture. This one is a CPU. This one is high-speed switching fabric. Simply you can think this one is memory, shared memory. And we learn about the difference of them and using different architecture in next slides. Let's focus on this one first. High-level view of generic route architecture, like this. Routing management control plane here. This is software. This one is special purpose single computer, you can think. But the main functionality is mainly for routing. This software is learning a little bit slower than this, operates in millisecond time frame. But this one should be very fast. That is operating in nanosecond time frame, because that packet should be forwarded immediately in very fast speed. This one is called high-speed switching fabric. This part is router input port, and this one is router output port. This is very simplified router's architecture. Let's focus on the left side, input port function, this part. We'll focus on this using this slide. This one is explained about input port functions. This is input port also. And the packet will be arriving here through this line termination. After that, link layer protocol, and this one is queuing buffer, and after that, this one will be sent to this switching fabric for proper switching to the proper output link. This one is physical layer, and this one is electrical signal, bit level. This one is receiving that bit level signal, and this one is data link layer. Think about Ethernet. We learn about this in chapter 6. Your slide may be different. That is wrong. We are learning actually in chapter 6 instead of chapter 5. This one is decentralized switching using header field values and lookup output port using porting table in input port memory. That is called match plus action. And the goal is to complete input port processing at line speed. If that is so slow, then that packet should be waiting here. Thus, this one is waiting buffer. Another word that is called queuing. Queuing is explained here. If datagrams arrive faster than forwarding rate, this is going out. And if that is much faster than this one, then forwarding, that is called forwarding rate, and the incoming rate is faster than that, then they should be stored there in this waiting buffer. That is queue, and that action is called queuing. Same figure, and this one is still explaining about input port functions. Using header field values, that is the information about the final destination. Lookup output port using porting table in input port memory. And as we learned already, traditional router is using this scheme, destination-based forwarding. That means forwarding based only one destination IP address. Traditional router is doing in that way. Now we are learning new scheme, that is software-defined network, and in other words, that is generalized forwarding. Port based on any set of header field values. We will learn about this any set. We'll learn this one later. This one is the destination-based forwarding, traditional router. Still we are learning. Most of our routers are learning in this way, even in our university. Here, this one is destination address range. And depending upon that range, the link interface is different. And depending upon that arrived package destination address, and that should be checked, and if they are belonging to this, and the link interface will be this one, and in that, through that interface, that will be forwarded. And we can think if that the range don't divide up so nicely, then for example here we can think this longest prefix matching. How's that? This longest prefix, this is address, that is front part, that is prefix, and the longest one, this one, longest one, longer than others. We are comparing until there, that is longest one. If that is matched, and then that is selected, that link interface will be selected, and that our packet will be forwarded through that link interface. Let's read this one first. When looking for forwarding table entry, this one, for given destination address, given destination is arriving packets destination address. We are using longest address prefix. This one is matched. That matches destination address. Let's assume one packet is arriving here. We are looking at two examples here. First example, one packet that is holding destination address. It's this one. And the front part is same, and this part is different. 0010 110. Neglect others, and let's focus on that. This part is that 000 10 110 00010. That is matched, and the others different, right? There is no 00010. This one is selected. Thus this one is selected. This one is the forwarding link interface, and our packet will be forwarded using this link interface. And let's assume other packet that is holding this destination address. Let's focus on this. This destination address is like this, 0001100, and that will be compared here, and that's different because that is 11000, and 11 also 11, those are same, but we are comparing more. That is called the longest prefix. This one is longer than this, right? Then this one is the longest prefix. If that is matched, then that will be selected instead of this. Thus, this one is using the interface number 1 instead of number 2. That is called the longest prefix matching. Let's look at switching fabrics. Switching fabrics are transferring packet from input buffer to appropriate output buffer. And the switching rate, that is the rate at which packets can be transferred from input to output. This one is often measured as multiple of input-output line rates. For example, n inputs, switching rate n times line rate desirable. For example, this one is switching fabric. This speed, switching speed, in terms of performance, that should be higher than each individual speed. If there are n inputs, then switching rate n times line rate. This one is each line rate, and this speed should be faster than this 1, 2, 3, higher than that. The interface, this line rate, and the switching fabrics speed, that should be higher than aggregated line rates to get the proper performance. And there are 3 different kinds of architecture here in terms of that switching fabric. One is memory, simplest one, and another one is bus architecture here, like our computer bus. And this one is crossbar. This one is highest speed. This one is higher than this. the speed is rate is this like this, and more expensive. This one is more expensive than this. This one is more expensive than this architecture. This one is explaining each one. First one, memory. This one is the switching fabric. Let's go back. This one is explaining about this. First generation routers. This one is the simplified one, and very similar to the personal computer architecture. This one is traditional computers with the switching under direct control of CPU. Packet copied to system's memory, and here, if packet is arriving through this input port, then that will be copied here, and another packet that will be stored there, and later that will be go out through this output port. Speed limited by memory bandwidth. Here we are focusing on the speed. Here, two bus crossings. First one here to arrive there, then to store there, and later to go out from this memory to output port. Two bus crossings, that is 1 and 2 per datagram. This one is called system bus, and we are using this as architecture. And our architecture limitation is based on this memory bandwidth usually, because that is being shared. Thus, at the same time, that cannot be used. Thus, if one is using here, then another should be waiting for that. And if that another one is being used, then this one should be waiting for that, because that is single resource. And there's some bus contention here, and resource contention. Resource is memory in this architecture. And this is another architecture using burst. This one is providing higher performance and more expensive than previous one. Datagram from input port memory to output port memory by a shared bus. This is input link and output link. Here, this one is bus architecture. And if they are going out, then they should pass through that bus. That is called bus contention. And that will be shared. There is some bottleneck depending upon the contention. Conflict. Bus contention, that is called bus contention. Switching speed limited by bus bandwidth. If that speed is high, then the architecture speed will be high, depending upon that speed. If that is so slow, then the overall performance will be so slow. Usually Cisco model number 5600. This one is using this architecture, and this one is providing 32 gigabps per speed. This one is sufficient speed for access and enterprise routers. Previous one, this one will be enough for our edge router. Usually in our university, we are using in each lecture room or right after the switch, this router may be used, and that speed will be enough to take care of them. But intermediate routers in our whole university networking architecture, then higher speed router speed should be used than this bus type, or next one, crossbar, this one, that will be used for the backbone router. This is another architecture, overcome bus bandwidth limitations. Thus, this one is providing higher performance, higher speed, and more expensive. Depending upon that crossbar architecture, Banyan networks, crossbar, are the interconnection networks initially developed to connect processors in multiprocessor. A long time ago, multiprocessing architecture, those are using this kind of crossover interconnection architecture. That is called multiprocessor architecture in the computer architecture. But that concept will be used in our network router architecture. This one is advanced design, fragmenting datagram into pixel length cells, switch cells through the fabric. If we are using this advanced design, then these cells that will be used for better speed. Cisco 12000, this router is using this architecture. You can observe the number of the model. If that model number is higher, then that is providing higher speed and more expensive. This one is providing the switching capability of 60 gigabit pairs through the interconnection network. Okay, this one is explaining about the input port here. And this is switching fabric. And this one is output port. Fabrics lower than input ports combined speed. This one is lower than this. Then we need to store there. That is called queuing, as we learned already. This one is explained again and focusing on that queuing. Queuing may occur at input queues. Here, queuing delay and loss due to input buffer overflow. This is input buffer. And the head of the line blocking. This one is the line. And this one, first one is the head of that line. And this one is explained about that. Queued datagram at front of queue prevents others in queue from moving forward. Okay, this one is explained about that. Even though that is a little bit complicated, not complicated, it is conceptually very simple. Okay, think about this case. Output port contention. They should go through this switching fabric, and they are going to this open link and output port. And both of them, they are going there. Here only one red datagram, this one, can be transferred. Let's assume the first one is going first, and the next one should wait. Then, because of this next one, head of the line blocking, that is waiting for that. That is called HOL, head of the line blocking, because of the first queue, the segment. Because of this first datagram, still this one is waiting in this buffer, thus this one is waiting for that and blocked. That is called head of the line blocking. Okay, this one is explained a little bit more. In next step, this one will be here, and this one should wait. One packet time later, green packet, this one is waiting for that. And that waiting is called head of the line blocking. That is blocked because of this. Output port. Let's focus on the output port in this case. Left part was input port and switching fabric after that. And they should, the datagram should go out through that link interface, but before that they should wait because there is some time difference between the output speed and the output from this switching fabric. That speed is different. Those intermediate buffer here, that is queuing buffer for output. Buffering required from fabric faster rate. This one is very fast, and this one is so slow. Then we need to use this buffer that is called queuing, as we learned. Datagram packets can be lost due to congestion, lack of buffers. If there is no buffer, then the packet datagram will be dropped. If we are using some scheduling scheme, among many datagrams, to send first, that is called priority scheduling. That means who gets best performance. That is related to the network neutrality. And here you don't need to worry about that. Usually the first one will be sent first. That is called like FIFO. FIFO means first in, first out. First in and first out. We are using that kind of normal scheduling scheme, FIFO scheme. If we are changing that order and using that scheduling, then that is priority scheduling. Depending upon that priority, we are changing that order to send out through that link line interface. Then that is called priority scheduling. But normally, as I mentioned already, we are using FIFO scheme. Okay, this one is explaining output port queuing. Here, let's focus on this. Buffering when arrival rate via switch exceeds output line speed, and queuing delay and loss due to output port buffer overflow. If the buffer is not enough, then that cannot be stored there. Then the datagram will be dropped, overflowed. Okay. In next lecture, we learn about the Ethernet cable that is called UTP, unshielded twist pair, and how to make. This is RJ45 connector. And if we are using UTP cable, Ethernet cable, and there is some colored lines like this, actually 8 lines, 4 pairs, those 8 lines, and there is some standard. We learn about that. And there is there are 2 types. One is T568A and T568B. When we are making normal plain Ethernet cable, we are using this T568B in both sides of one link on Ethernet cable, one end and another end, this one. And I will show you later in detail about this. I'll wrap up today's lecture here, but we'll continue from this one in next lecture.